First keynote of the morning, and it's my pleasure to welcome Riccardo Mariani, who is the Vice President of Industry Safety at Nvidia. He has joined us from Italy, where it says 6 a.m. early morning for him. He has also sent a recorded video, so we'll play that, and then he'll be available for Q&A. But before that, let me introduce Riccardo to those of you who haven't interacted with him earlier. Riccardo is recognized as an expert in functional safety and the IC reliability. He is serving as VP of Industry Safety at Nvidia, responsible for driving safety alignment across Nvidia's automotive and embedded business units. He is responsible for developing cohesive safety strategies and the cross-segment safety processes, architects, and products that can be leveraged across the Nvidia's AI-based hardware and software platforms. Prior to Nvidia, he was the Chief Functional Safety Technologist at Intel, where he saw the strategies and technologies for the IoT applications that required the functional safety, reliability, and performance. In the field of autonomous driving, transportation, and industrial systems, he is the first Vice President for the standard activities of the IEEE Computer Society, Chair of the IEEE P2851 Standard on Safety Analysis and Interoperability, and also the chair of the IEEE Initiative on the Reliable, Safe, Secure, and Time-Deterministic Intelligent Systems. Riccardo has spent the bulk of his career as CTO of Yogitech, an industry leader in functional safety techniques. Before co-founding that company in 2000, he was the technical director at Aurelia Microelectronica, where his responsibilities including leading high reliability topics in projects with CERN in Geneva. A prolific author and a respected inventor in the functional safety field, Riccardo has contributed to multiple industry inventors in the functional safety field. He has been, which has led to the overall the ISO 2626211, the part 11, which is specific to semiconductors. He has won the SGS Thompson Award and the Enrico Denot Award for his engineering achievements. He holds a bachelor's degree in electronics engineering and a PhD in microelectronics from the University of Pisa, Italy. Welcome, Riccardo.
Hi, everybody. I'm very happy to be here. Thanks for the introduction.
Thanks. Samir, we can play the video.
Hello, ciao. I'm Riccardo, VP of Industry Safety at Nvidia. My goal for today is to give you an update about a first-of-its-kind software-defined computing architecture that includes the most powerful computer, system software, and application for consumer. It's really marking a turning point of traditional vehicle becoming high-performance, updatable computing devices. I also want to show what does it mean to make them functionally safe from end to end and top to bottom. A few days ago, in a live stream media event from Stuttgart and Silicon Valley, Mercedes-Benz CEO and Nvidia founder and CEO Jensen Huang announced that the automaker will launch software-defined intelligent vehicle using end-to-end Nvidia technology. So I want to show you a video in order to explain what this does mean. So, as you have seen in the video, the advancement and the breakthroughs in AI and computing are opening future fleets to dramatic new functionalities, fundamental transforming the vehicle architecture for the first time in decades. And this transformation is occurring rapidly. The market for AI hardware, software, and in-car services is worth about $5 billion today. By extending these capabilities to a fleet of about 100 million vehicles, the market has the potential to grow to $700 billion. So like all the modern computing devices, these intelligent vehicles are supported by a large team of AI and software engineers dedicated to improving the performance and capability of the car as technology advances. This software-defined architecture is also opening up new business models for automakers. Mercedes-Benz can add capabilities and service over the air at any time to the life of not just one customer, but across many customers through the life of the car. So now I want to dive in some of the key technical technologies characteristic of an autonomous driving architecture. So, as said, the car of the future will be software defined and must be ready to run future applications that in some cases have been envisioned yet. So given this is a new world, the OEM, they need to plan for the unknown apps of the future and builds headroom in today. With an open architecture and platform, you can support new features, for example, with an over-the-air update. So centralizing and unifying the computing in the car will make it easier to integrate and update advanced software features. For all those reasons, from our view, to be widely deployed, an autonomous driving architecture must be a platform rather than a collection of disjoint elements. If we start from the bottom, at the foundation we have the integrated circuit. So in our case, the drive architecture use Orin and Ampere architecture. Those new SoC that are based on Ampere, and they extend from ADAS and CAP to autopilot on a single architecture. As you can see, from ADAS to L2 to L5, from windshield and CAP to robotaxi, with a single scalable architecture that leverage software development across the entire range. And if we zoom a bit in on the Orin, the complexity of Orin is 17 billion of transistors. So it's the world's most advanced AV and robotic SoC. It includes 12 Hercules ARM64 CPUs. It includes Tensor Core GPU, DLA, PVA, and many other interfaces. As also from functional safety, is capable of AZD for systematic and AZB for hardware random failure, as I will explain later. So on the foundation of the integrated circuit, we need a complete software stack. So in our case, it's drive stack. That open and scalable software stack begins with applying DNN to complex sensor data to allow autonomous driving. Then it fuses the computer vision, graphics, and AI to create the next generation of augmented reality interface with information like the different point of interest, alerts, and navigation. So then on top of autonomous and augmented, It uses AI capabilities to deliver a co-pilot type of support for driver inside and outside the car. So, I mean, artificial intelligence, it's really at the core of that autonomous driving architecture. AI fuels and gives flexibility to all the major functionalities of an autonomous driving architecture, from the perception to reasoning and driving. It also enables most of the underlying technology that are required by an autonomous driving architecture, such as HD map and mapping. So the AI computing is really a fundamental characteristic of an autonomous driving architecture. In that sense, the transportation industry has recognized that AI computing in the vehicle enable also redundant and diverse software algorithms to deliver increased safety on the road. And this is what we as Nvidia, we deliver with our open and scalable architecture. So in order to give you another example, I want to show a video on one of the AI-based functionalities.
Hello, everyone. We hope that you are staying healthy, staying safe. We are working from home, so welcome to Drive Labs, the home edition. And today we're going to talk about using a deep neural network to understand the structure of an intersection. So things like how many lane lines are there in each direction? Where are the intersection entry and exit lines? And the application for this is autonomous intersection handling in both semi-urban and urban scenarios. The DNN is able to detect and classify different types of intersection structure features, including intersection entry line points for the ego car, shown in red, intersection entry line points for other cars, shown in yellow, and intersection exit line points for all cars, shown in green. The DNN also detects non-drivable lane lines, as shown in black. We see that the perception is robust to both partial and full occlusions, and that the DNN is able to predict both painted and inferred intersection structure lines. We also note that these are all per-frame DNN detection results, with no tracking or fusion of any kind applied. The ego car can determine where to stop for the intersection based on the closest intersection entry line, and can decide how to exit the intersection using all of the intersection exit line information. So in this case, the DNN correctly predicts that the ego car could exit the intersection by either proceeding straight through, taking a left or right turn, or making a U-turn. And we also know that this perception information can be used to extrapolate how many lanes and which types of lanes the intersection has. These DNN perception results can be used in several different ways for autonomous intersection handling. They can be used to generate paths to navigate the intersection. They can be used to create a map of intersection structure. And they can also be combined with previously mapped results, where available, to create additional diversity and redundancy.
Okay, another aspect that I want to show is that to be complete, an autonomous driving architecture should be also end-to-end. What I mean is that on top of the hardware and software architecture, on top of all the AI functionalities that I haven't shown, so this architecture has to provide an end-to-end infrastructure to collect data, to train models, to simulate them. In addition to accelerate developments, the use of our already trained DNN is also key. In fact, we recently announced we are delivering the transportation industry with access to our DNN for AV development. By delivering those DNN and also the advanced learning tool to optimize them for multiple data sets, we are enabling shared learning across different companies and countries while maintaining data ownership and privacy. So in this way, we are really accelerating the reality of global autonomous vehicle. So given the complexity of the autonomous driving architecture, as we have seen, it is very important to have an end-to-end infrastructure that covers architecture design and validation. If we focus on validation, validation by simulation is very important. Simulation can help us to understand the possible behavior and outcome of the autonomous driving architecture in a virtual setting that we can directly control. A simulation may consider an entire system like a full vehicle with tires and automated driving system function, or a subsystem with an actuator and a controller, or a component with sensor and buses. To expand on this a bit more, while Nvidia and other companies, they still have AV test fleets that are on the roads across the globe, recording many miles of real-world experience, it's definitely impossible for these tests to cover every situation that a self-driving car may encounter, or repeat these scenarios under a wide range of conditions to ensure the autonomous vehicle can handle them. So with our Nvidia Drive Sim, we deliver a way to test the self-driving technologies in any different weather, condition of traffic or location, as well as rare and dangerous scenarios, and it's very scalable. So now, in order to explain you a bit the feature of that environment, I want to show another video. Okay, so now I want to deep dive a bit on functional safety. That is one of the key properties that an autonomous driving car requires. So let me start with some definitions, start from the bottom. In order to design for safety, we need to avoid or mitigate different things, starting from systematic failure, for example, bugs in hardware, software, or tools, or then hardware random failures, for example, aging effects in the field or soft errors. Then we also need to control performance limitation like weather, such rain, sun, fog, misinterpretation of image. Then we need to consider reasonably foreseeable misuse or incorrect HMI, confusion of the user, user overload, as also impact from surroundings, other users, impact of infrastructure, additional environmental conditions such as AMI. And eventually also, of course, successful attacks exploiting the vehicle vulnerability. So the first two are what we call functional safety. The other three in the middle is what we call safety of the intended functionalities or SOTIF, and then we have cybersecurity. So without going too much into detail for the purpose of time, I want to share with you an overview of the standardization landscape on functional safety for autonomous driving vehicle. And I want to start with a look of the foundation of that standardization landscape. Starting from the bottom of the slide, you see the ISO 262 standards. It gives the infrastructure to handle functional safety. As I have shown earlier, this is with respect to the process requirement and to type of failure, the systematic failure and the hardware random failure. The standard it covers from item, function to semiconductor. On top of the ISO 262, we have the ISO 21448 that covers the safety of the intended functionalities or SOTIF. It mainly addresses the limitation of functionality, as I have shown. It also has an annex that covers artificial intelligence. On a contiguous but very critical field, the ISO SAE 21434 covers cybersecurity engineering. So given that the autonomous driving vehicles are more and more connected and therefore can be exposed to threats. Similarly to the ISO 262, the ISO SAE 21434 looks at the entire process and life cycle of a vehicle. It follows the V model. During all phases, including requirement engineering, design, specification, implementation, test, and operation, security aspects need to be taken into the account. So ISO SAE 21434 has specific requirement for software development, including analysis to check for inherent weaknesses and the overall consistency, correctness, and completeness with respect to cybersecurity requirement. So guidelines on software coding like the MISRA C and CERT-C are recommended typically in ISO SAE 21434. On top of those foundation, we have a few ongoing application specific standardization initiative. The aim of them is to deliver detailed requirement, including architectural guidelines for the autonomous driving vehicle. Starting from the top, the ISO TR 4804 is based on the SAFAD white paper. It covers safety and security for automated driving system, including design, verification, and validation methods. The document has been just finalized and we publish it soon. It has a different chapter and annex, or also one annex on artificial intelligence. The UL 4600 covers the safety of the evaluation for autonomous vehicle products and concentrate on ensuring that a valid safety case is created. A safety case includes three elements: goals, argumentation, and evidence. And those are addressed by the UL 4600. Last but not least, let me mention an important and recent joint ISO and IC initiative named ITC SC42 on artificial intelligence, with a working group handling the trustworthiness of AI, including functional safety on AI-based systems. It is jointly working with the IC 6158 working group on that topic of AI safety. There are also a set of supporting standardization activities that cover detailed aspects of safety. Those are some of the ones that are driven by the IEEE. The IEEE P2846 is about formals, methodologies, and model about autonomous driving architecture decision. The P1228 is a standard from the IEEE for software safety that was created several years ago for other industry and now has been refurbished for autonomous driving architecture. But let me spend a few more words on the P2851. Its aim is to standardize functional safety analysis and functional safety verification with focus on facilitating data exchange and interoperability among those analysis and verification activities. Initially, its scope was mainly integrated circuit, but now it has been expanded to items, system, and software. I'm chairing this standard, and so feel free to contact me offline if you are interested in discussing further or helping. So there are also a set of industry connection activities. In fact, architecting an autonomous driving system involves so many aspects, and therefore the collaboration among industry is very important. By industry collaboration, we can identify gaps, guaranteeing diversity of solution without making a confusion in the market with diverging approaches. And of course, we must update standardization activities according to the evolution of technologies and the experiences in the field. Some examples are the newly formed industry connection activities launched by the IEEE on assessment of standardization gaps for safe automated driving that I'm driving, as well as the ISO TR 4609 on standardization for autonomous vehicle. SAE has also a similar initiative. So now that I have given a bit of a background on functional safety standard, I want to invest some time on functional safety architecture. So, of course, the autonomous driving architecture shall be functionally safe, and up to a certain extent, it's also need to be be able to tolerate faults. The described software-defined architecture supports several hardware architecture. One of them is shown here. This hardware architecture is built by two channels. We call it channel. One is the primary channel, and one is the backup channel. They both work on a subset of sensor suite, and they both have a path as a monitor path. This architecture can support what we call in ISO 262 ASIL decomposition. So, for example, its channel is built to support at least ASIL B out of D. The ASIL in the ISO 262 is a level of safety that range from A, B, C, and D. Other levels of the ASIL decomposition are possible, for example, in the sensor input chain. This is the reason why achieving ASIL D for hardware systematic is key element to offer flexibility of system architecture. As mentioned in Nvidia case, we got approval from assessor for our ASIL-D systematic and ASIL-B for hardware random failure. Now, if we focus on the monitoring idea, our view is that should be based on a comprehensive approach that it should cover mainly 3 levels. These 3 levels are addressing different type of failure at different level of the stack. Starting from the bottom, we have a level addressing hardware failure. So failure of SoC, sensor, so buses. In these cases, we have low-level hardware diagnostics such as hardware ECC and lockstep and self-checks, as also things like the monitoring of a flow of a program like Watchdog. On top of that, we need to detect failure of software OS and drivers, as also then function level issues and system level issues and failures. This is why we can have a local monitor that is somehow doing monitoring of the function level, such as output validity and cross-check and valid output trends. As also we can have system level type of a monitor, such as a monitor on trajectory and commands and monitor on collision avoidance. The safety analysis methodologies identified in the previously mentioned standardization activities are very important because they are used to identify all the potential failure in the system such that those failures can be detected and mitigated. So detecting a fault is not enough in autonomous vehicle, so emergency operation is also critical in any autonomous driving architecture. You can have, in fact, you can have some failure leading to recoverable system degraded operation or non-recoverable system degraded operation or to system emergency operation. So having this variety of effect, you need to have a variety of reactions. So you need to implement different system state, like either to complete the mission despite the failure, or drive to safe harbor, or drive to shoulder, or stay in lane. So this is a key aspect for degraded and emergency operation. Now, as we have seen, AI, it's at the core of the autonomous driving architecture. So it's really required that we deliver functional safety and safety of the intended functionality for the whole AI technology. So that means that we need to implement safety, for example, quality of the process and software on the data factory, starting from the route planning, data collection, ingestion, metadata labeling, curation data labeling, training and VMV test, dataset aggression, and of course the training of DNN. But that is not enough. We need to deliver the confidence in use of the tool use, like, for example, the planner, the tools and AI infrastructure. As also, we need to guarantee the correctness of the implementation of the inference engines and the runtime algorithm and DNN. As also, we need to be sure that our DNN verification and validation approach, VMV, is done according to the ISO 262 and SOTIF. So, in summary, it's really a combination of many different things, from hardware to the software stack that should be autonomous, augmented, and assistive, that create the condition to have a software-defined, AI-enabled, end-to-end, and functional, safe, autonomous driving architecture. I hope I give you some inputs in my talk, and I want to finish with another video. Let me show that. Okay, I hope you enjoyed my talk, and thank you for the attention, and have a good day.
Thank you very much, Riccardo. That was an awesome update to give us a very broad view of, how the whole autonomous driving is coming up and the mix of software and hardware. So at this time, while we launch the poll to get a quick feedback, Kavita, do we have any questions?
Sure. I think Riccardo answered one. There's one more question that Riccardo wanted to take live, but I will read it out. For ASIL-D components, are hardware testing enough, or are there guidelines for software testing that need to be met?
Yes, I think it's a really good question, so I would like to answer live. So it's always a combination between hardware and software that we need to do to achieve the ASIL-D level. And I assume the question is related to testing of hardware failure using software. So yes, so definitely you typically need software-based tests to test either your core, your CPU, or your GPUs. You do that. You may also have software redundancy, for example, running 2 copies of the same function in the same core and compare. Or you could have more advanced, I would say, redundancy, like diverse algorithm operated in the meantime. Or you could have also software-driven tests for faults like latent faults in CPU and memory. So definitely yet. And those guidelines you can find in the ISO 262, the chapter 11. This is where we have, for example, the list of the fault model and failure mode that either you need to detect with hardware or software tests.
Thank you. One question from my side, Riccardo. I think while I was following you, means the silicon part or the chip part for these applications, if we put together, I think we see there is everything that we have designed till now will have to be implemented in these silicons, right? Whether it is the performance, the power, the security, the safety, reliability, and all of that, right? Now these chips will be more implemented as an ASICs for the specific use, or do you foresee that we can end up creating some things like a standard products in the future?
So I think there will be different things. So for something like I have just shown, I think the system on chip with a dedicated accelerator is what it will be somehow the reality. Then there are dedicated ASIC will remain for sensors, for things in which you really need to have a dedicated type of functionalities. There are also options for general purpose SoC or FPGA for dedicated, for let's say for more open architecture, but definitely I see the direction of system on chip is the main one, especially if you need such kind of a performance and combination of different interface in accelerator, and you need to have really a thread of that. I mean, the investment and the cost to make them safe and secure is such that you really want to have a family that is covering scalably from the L2 automated up to L5 automated vehicles. So this is why you need to have a family that is scalable across the different AED applications.
Okay. Thank you. Any other question, Kavita?
No, actually, there are no more questions.
Okay.
Okay, there's one more that just came in. Are vehicles of smaller dimensions a challenge?
So I'm not sure exactly what does it mean a challenge or dimension, but I would say that of course some of the most advanced autonomous vehicle functionalities will start to be applied to the bigger vehicle, either the high range or even in terms of dimension, you can think to trucks. But still, we want to achieve at least the basic of the NCAP and ADAS function to any small vehicle. And in some sense, the challenges are similar. So in the standard, there are no, there are no requirements depending on dimension, other that, of course, if you move to a truck or a trailer, then you have some additional things to be considered.
Very good. Thank you so much, Riccardo, for taking your time to give us this a very top-level view, but an end-to-end view of what an autonomous car would look like, because that way now we can connect to the whatever work we do, whether IP, SoC, test, CAD, and others, that how do we go and affect that the big ecosystem that the world is building. Just to thank you for your participation on behalf of the committee and all the participants, I would like to thank you for taking your time early in the morning and presenting this to us, answering these questions live. Appreciate your time. Thank you so much.
It's my pleasure. Enjoy the rest of this great conference.
Thank you.